Hey AP Chemsters, this is Mrs. Vanderlei bringing you Blankwalle 16.5. This is all about solubility, equilibria, and the solubility product constant. So we just got through with the buffer section, and now we're kind of switching gears and talking about like precipitates and forming a solid in a double replacement reaction, that kind of thing. We have learned way back in chapter 4 about some of the solubility characteristics like sodiums and potassiums and nitrates. They're always soluble, but let's say lead sulfate is not. We call that insoluble and will form a precipitate. We would talk about those reactions going to completion, but the question is, do they really go to completion? And the answer is no, it doesn't go to completion. It actually goes into an equilibrium, a dynamic equilibrium. And so what is dynamic again? It keeps moving, it keeps going in a sense. And so in a dynamic equilibrium of forming a precipitate, of having a solid in solution, what's the dynamic process? What's the forward? What's the reverse? Well, in this case, having the solid go to the aqueous is dissolving, and then the opposite is having the aqueous ions here forming the solid or crystallizing. And so overall, it is an equilibrium setup. And a great visual for this is making rock candy. I don't know if you've ever made rock candy. That'd be something fun to do. Maybe we should do it in class. But if you were to make a rock candy solution, you take a certain amount of sugar, you boil it, and so you have a supersaturated solution, and you put then a string in it, or a piece of wood if you want. You want to be really artsy or something, and you let it sit there. And what happens is that the crystals will form onto that site of nucleation, either the string or the piece of wood. And you can get a whole bunch of crystals out if you leave it in there long enough. Now, what most people do when they make rock candy is they leave it open to the atmosphere. And so then the liquid will evaporate, and that's that. And in that sense, it does go into completion. But what would happen if you were to put a lid on your rock candy? All right, you're still going to get crystals formed, but you're not going to have the solution evaporate. You're going to keep like a terrarium in a sense. All right, some will evaporate and then some will recondense again, another equilibrium setup. But what happens then to the rock candy itself? It will undergo what's called a dynamic equilibrium. Some of that rock candy crystals that you have created will be redissolved back in the solution, but guess what? The sugar in solution will recrystallize back into the rock candy. So it looks like nothing's going on, but in reality, you have that going into solution, going out of solution, going into solution, going out of solution, all right? So that's what we mean by a dynamic equilibrium. All right, and this will occur when what? The solution is saturated, all right? Or in the case of your rock candy, that would be supersaturated. And then what happens that enough crystals will come out of solution until it becomes saturated. And that's where equilibrium will then occur. Okay, so you have a net result of no change in the amount of precipitate, although you're always having the crystallizing and the dissolving, the crystallizing and the dissolving, okay? All right, so down below here are some pretty clever looking pictures. So this picture is that of salt, I assume NaCl. And so here you put your initial amount of salt into the water. You put a lot of salt in the water, let's put it that way. And so what happens, a certain amount of the chloride, which is the big blue purpley one, and then the little sodiums, all right? So they're going into solution, all right? And that's what you see right here. But once you have a saturated solution that the liquid part is holding as much of the ions as possible, what happens? Those that come out, others go back in. So here's the one they're recrystallizing, all right? So the arrows going out is the dissolving, and the arrows going in is recrystallizing. So this is at equilibrium. Notice that I have the same number of arrows going out as I have the same number of arrows going in, all right? So that's your dynamic equilibrium. And so there is two very important terminologies coming up, all right? And that is, number one is KSP, all right, which is another K value, just like Ka, just like Kb. This is KSP. So this is the solubility product constant. It's the equilibrium constant for a chemical equation. representing the dissolution process, the dissolving process, all right? So what goes into your law of mass action? Not the solid. Notice the solid doesn't go in there, but you have your aqueous, all right? So here's your KSP. Just like any equilibrium expression, if you have a coefficient, you have to square it. Experimentally determined solubility of an ionic solid can be used to calculate its KSP value, and the solubility of an ionic solid can be calculated if its KSP value is known. So what did I just say here? The solubility of an ionic solid. Well, what's solubility? It's a concentration. It's a moles per liter kind of a thing, all right? And they have a special name for that, and that is called molar solubility. Hopefully that makes sense to you, all right? It is how many moles per liter are in the solution, all right? And you can calculate the molar solubility directly from KSP. This is your X, and this is what I mean. You have two terms you have to keep straight in your mind. So are they asking for KSP? They're asking you to solve for like Ka or Kb or KSP. If they're asking you for molar solubility, that's your X. Folks, this is an equivalent to like talking about the acids and bases. So I can either give you Ka and you solve for pH, or I can give you pH and you solve for Ka. The idea of the pH, which is your hydrogen ion concentration, that was always your X, wasn't it? Well, that's what the molar solubility is. It's your concentration of your ions in solution. It is just X, okay? So let's try an example here, okay? So if I have silver chloride, let me get this set up for you. Right? It says, as the system is in what? Equilibrium. Well, what do you have to fill out? An ice table, right? But what's the beauty of this? This is a solid. You never include that. So just like we've always done before, in the case of silver chloride, you have 0 to start with, like we just put all the silver chloride in the water to start with immediately. And then you're going to add positive X, and then you can solve for X, all right? So when you solve for X, that is molar solubility. So what is the unit of X? It's moles per liter. I hope that makes sense for you, okay? Now, what could I do at this point? If they asked me for molar solubility, could I solve for it? I sure could, all right? Because here's my KSP value, and then I would set it up, okay? So here, watch this. All right, so let's go ahead and do this, all right? They gave you the KSP, so I'm going to set my law of mass action. KSP is equal to the concentration of the silver ion times the concentration of the chloride ion. Well, hey, they're both X, right? So they're equal to 1.77 times 10 to the negative X, or 10 to the negative 10 equals X squared. Hey, so what's X going to equal? If you have a calculator, go ahead and do it, but use some mental math, right? This is an even number here. So we know that the square root is going to be 10 to the negative 5th, and this number is between 1 and 4, so my answer is between 1 and 2. So yes, if you use your calculator, let me scroll up just a tad, whoops, the other way. Oh, okay, I'll just do it this way. So your X is equal to 1.33 times 10 to the negative 5th molarity. Notice I put my units in there, all right? So what does this mean? If I took a liter of this and I made a saturated solution of silver chloride, what does that mean? I can't put any more solid in there, all right? What's the concentration of my silver ion? 1.33 times 10 to the negative 5th, that's not much. All right, what's the concentration of my chloride ion? 1.33 times 10 to the negative 5th. Again, that's a pretty small molarity, isn't it? That's why we consider silver chloride to be insoluble. Okay, let's go on to the next page. All right, so here's a list of the selected solubility constants at 25 degrees Celsius. Oh, wonder why they gave me the temperature. Because let me guess, I bet if we were to change the temperature, we would change the KSP. Oh yeah, that's true, that's right. So anyway, here's a list of them. So maybe use this as a reference. You'll probably have to go back and look for values throughout this section here. So, put your paper clip or something on this chart, okay? So problem number 15 says, all right, let's calculate the molar solubility of lead 2 chloride in pure water. So what do you think the very first thing you ought to do? Hey, write down the equation for the dissociation of lead 2 chloride. Go ahead and do that and be very, very careful of your coefficients, okay? Pause this and write down that equation. All right, hopefully you got something along that line. Why did you have to be so careful? Because this coefficient's a 1 and that's a 2. So now what? It's an equilibrium setup. You have to set up your ice table, right? So here is, whoopsie, here is your, no, there's not it. There it is. Here's your ice. Hey, what do you think I can do? I didn't put, whoops, I didn't put this down, but isn't lead 2 chloride a solid? And aren't these aqueuses? All right, yes, they are. So when we start off with, these are 0. Now be super duper careful, okay? What's gonna happen here? This is gonna be plus x, and this is plus 2x. So what does that mean? That when it's all said and done at equilibrium, how much of these things do I have? I have x and 2x. Okay, so let's set this up. So the KSP is equal to lead plus 2 plus chloride squared, right? Well, what's lead? X. What's chloride? 2x. So what is 2x squared? Well, here I put the numbers in. And what is 2x squared? 4x squared. What's 4x squared times x is 4x cubed. All right, so then when we solve for x, ruh-roh, what do you notice? This is an odd exponent. So if I make this, it's 11.7 times 10 to the negative, what would that be? Negative 6. So what will that become? That will be something to the negative third. All right, so check this out. Actually, I misspoke. I was doing a square root, didn't I? Holy cow, it's a cube root. So what's the first thing you do? Divide by 4 and then take the cube root, okay? So here is when I divided by 4, okay? And then this is when I took the cube root, okay? And now what? This is the molar solubility. That's what they're asking you for. So what is the concentration of lead? Well, it's 0.0143, right? Well, what's the concentration of chloride? Well, I multiplied that number by 2 and I got 0.0286. If they asked for just the molar solubility, you can stop right here and I would put a molarity sign after that. They could ask for what is the concentration of lead ions, what is the concentration of chloride ions, all right? And then you'd put the molarity sign. Why don't you go ahead and start problem 16 all by yourself, and when you are totally done, come back, okay? Why don't you do that for me? All right, this is what I came up with. Here's my iron 2 hydroxide. Notice it's my solid. I have, again, my X and my 2X. So my KSP is iron 2 plus times hydroxide squared. So you end up with 4x cubed again is equal to the KSP. I got that from the chart above. When I took divided by 4 and took the cube root of it, I got 2.3 times 10 to the negative 6 molarity. That is my molar solubility. So if they asked you, well, what's the concentration of iron ions? It's 2.3 times 10 to the negative 6. If they asked you for hydroxide, it's 4.6 times 10 to the negative 6. Okay, let's do one more here. And I crossed this out. I didn't want to do copper 2 iodate. Why? Because it's going to be the same exact setup. It's going to be 4x cubed, all right? So why don't you cross out the copper iodate one or copper 2 iodate one and just do iron 2 carbonate. Just do that one. And it's going to be a little bit different setup, and that's fine. Go ahead and do that. And when you are done, come back. All right, so here is my setup. Hopefully you got this. So now it's just an x squared is equal to the KSP. And I took the square root of both sides and I got 5.54 times 10 to the negative 6x. And that is your molar solubility. If you want to put a little molarity in here, that'd be fine. And then these are the concentration of the ions of iron and carbonate in a saturated solution. Okay, this is a good place to stop. We're not done with this section, so look for a part 2. But in the meantime, hey folks, don't wait to be great. See you shortly. Bye-bye.